Hello everyone, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. Welcoming you to the class of vector spaces. In this class, first we introduce vector spaces and we discuss the importance and why we need to learn vector spaces. Later, we will have a detailed definition of vector space. After that, we will prove two concepts. One, zero vector in every vector space is unique. And the next one is negative of a vector in a vector space is unique. Later, we do some properties of vector spaces. Finally, we do some assignment problems in this class. Let us first move on to the introduction of vector spaces. We can visualize R2 and R3 geometrically. R2 is nothing but XY plane. We do a lot of maths in XY plane from 9th standard onwards. R3 is the 3D space, XYZ space. All real objects can be identified in R3 space geometrically. In this chapter, we extend that R3 space into n-dimensional space. If an object has some more dimensions, that is, it may have some smell, it may have some color, weight, time, speed. If we have to calculate all this in addition to their position, we need a bigger space, multi-dimensional space. So here we can find a space with n-dimensional space, and it can be any number, any kind of number. So in this chapter, we can get an idea on R or simply we can call it as Rn space. The study of vector space is not much different from the study of Rn. If we understand Rn space completely, then most of the vector spaces are similar to So vector spaces are used in engineering, physics, statistics, and every branch of science. In fact, in the modern world, everyone wants the actions at their fingertips. To do the same, lot of digitalization is needed. So if we speak something, Google recognizes your speech. So your speech will be converted into numbers. That numbers will be identified by Google ultimately. So in all the digitalization process, all the actions are converted into numbers. In all these actions, the role of linear algebra is very important, and vector spaces are stepping stones in this direction. So if you have a clear idea on vector space, you can extend your knowledge in digitalizing the world, which is a very crucial thing in the modern world. Let us have a detailed discussion of vector spaces. A vector space is a non-empty set V of objects called vectors, on which two operations called addition and multiplication by scalars are defined with the following axioms. So vector space is a set. Basically, it is a set with some roots. We know that a set is a collection of well-defined objects. We need some elements in the set to do some experiments. That's why we are taking a non-empty set. We are naming it as V, the first letter of vector spaces. So vector space is nothing but a set with some roots. Here we have two operations, one addition and another one is scalar multiplication. So this addition can be any sort of operation satisfying the conditions given below. So addition may be some adding two chemicals, adding two signals, or anything. This need not to be usual addition. So we can take objects also. Actually, the set consists of any type of objects. The thing is, the objects are to be well defined. So here we call the elements of the vector space as vectors. So here we have two terms, vectors and scalars. Scalars, usually we take real numbers, but we can take any field which we come across in the group field. So usually we take real numbers, then we get a real vector space, but for simplicity, we can call it as vector space. Another term used in this one is axioms. Axiom is nothing but predefined rules for which no proof is required. So the vector space is a set, is a non-empty set with some rules. Rules on addition, vector addition, and scalar multiplication. Let us see what are the rules. For all u, v, w belongs to v, capital V is our set, and scalar c and d, we have the following rules. Here observe that we are using later part of alphabets as vectors and initial alphabets as scalars. We are avoiding A and B for some convenience. Later, in the later part, we use A and B as the components. That's why in the definition we have used C and D. You can use any of this. Say in textbooks to differentiate scalars and vectors. Sometimes we write the letters in bold, or we can put a bar. But all these just to distinguish the difference between scalars and vectors. Here I have taken UVW in the last letters of alphabets as vectors and initial alphabets as scalars. So we have the following axioms. The first one is U plus V belongs to V. So here addition plus symbol addition it denotes vector addition. Vector addition. So that may be defined clear to that any binary operation which satisfies all the following axioms can be taken. So here if I take V as a set of gases, I have taken let V be the set of gases. Let U is hydrogen and V is oxygen. And U plus V is water. Water is not a gas, so that is not in V. So that set does not satisfy this problem. So that is not a vector space. A vector space should satisfy all these conditions. Suppose I have taken colors. Let U be a red color and V is some blue color. If I add the two colors, I will get another color which is also a vector of V. Then that set satisfies this condition. So this condition must be satisfied. This is the first condition. In group theory, we call it as closure property. This is invented in binary operation. So the sum of two vectors, addition of two vectors must be in the same set. That resultant vector. You add two vectors, you should get the resultant vector is also in the same set. That is the first one. If you take two bacteria and add them, the result must also be a bacteria. That should belongs to the same group which you have taken earlier. Suppose I have taken some liquids, non-toxic liquids, as my group. When we say that it is a vector space, it satisfies all the conditions which we are going to discuss, as well as this first condition. So this first condition tells us that if we add any two non-toxic liquids, you will get a non-toxic. Once we have given the certification of a vector space. If it is a vector space, that is true. If it is not a vector space, we cannot carry. So that kind of assurance we can give to the systems. We mathematicians model the things. We create models which can be used for any purpose. Your vectors may be signals, chemicals, colors, bacteria, virus, anything. So we need to extend the concepts to that level. Not only memorizing the symbols, you have to extend the concepts to that level. This is the first property, and this is the second one. U plus V is equal to V plus V. This is commutative property, which can be found in abelian groups. This is brought a little bit earlier for the convenience. U plus V is equal to V plus V. So the order of the addition is not important. You can add in any order, the result will be same. In chemistry, we can find these situations. Sometimes, if you add two chemicals, you pour some chemical into another one, and reversing the order, the result will be different. You will come across such examples there. Another simple example is that if I want to take actions as my vectors. So U is wearing a socks today. Wearing a socks is an action that is denoted by U. And V is wearing a shoe. So U plus V means you are wearing socks and shoes. That can be done. But whereas V plus U is not possible. Once you wear a shoe, you can't wear socks. So here it is not possible or awkward. The situation is different. So here U plus V is not equal to V plus U. That should not happen in a vector space. So the vectors which satisfy these properties said to be hold this condition. So this is our second property. Now the third one, U plus V plus W is equal to U plus V plus W. In fact, operations are done between two vectors. U plus V will give a new vector that is added to W on the left hand side. On the right hand side, U is added to the resultant vector of V plus W. If you get same vectors both times, then we can say that this property holds. In group theory, we call it as associative property with respect to this addition. And now the fourth property, there is a zero vector 0 in V such that U plus 0 is equal to U. So we have additive identity in group theory. This is similar to that. We are denoting it by 0, but I will call it as O, as we are using U, V, W for the vectors objects. For the convenience, I will call it as O. In the later part of the theory, we use scalar 0 also. To avoid confusion between that scalar 0 and this vector 0, I will call it as O. So my 0 vector in V is O. So I can reread it. There is a 0 vector O in V such that U plus O is equal to U. So O does not affect anything. It will give you the original vector. It does not change the situation. So that is the 0 vector. It is similar to the identity element in group. A group. Now the fifth property is additive inverse there. Here for each U in V, for each vector U in V, there is a vector minus U in V such that U plus minus U is equal to O. O is my 0. So minus U is a vector which takes your vector U to the 0 vector. So it is a neutralizer, I think. It seems to be a neutralizer in any group, in a particular set. So it is like just like additive inverse and in group. We call it here, it is negative. Negative of U. Minus U is the symbol for that. Whenever you come across minus U, that means it is the negative of U. Negative of U means the vector which makes U while adding 0. U plus minus. In group theory, for these two definitions, you find U plus O is equal to O plus U is equal to U for identity. But here, we have already got this completive property. That's why it is not necessary here. Whenever U plus O is U, O plus U is also U by the second property. Similarly, U plus minus U is equal to O implies minus U plus U is also O. So that is not repeated here. So in the group theory, these 5 conditions, if a set holds these 5 conditions, we say that that is an abelian group. Abelian group with respect to that binary operation H. So these are the first 5 conditions of our vector space. All these conditions are related to vector addition. So the symbol plus, we can call it as vector addition. So V is, now we can say that V is an abelian group with respect to operation vector addition. Now let us introduce scalar multiplication. Let C be a scalar. Unless specified, C is a real number. So C times D, scalar multiple of U by C is denoted by Cu. Cu is also in V. So Cu is nothing but U plus and so on plus U C times. 10U means U is added 10 times. The resultant vector also is in V. So if you have 2 ml of oxygen in your group, in your set, if it is a vector space, you will get 10 ml of oxygen and 1000 ml of oxygen and so on. This can be simply written as Cu belongs to V. Cu belongs to V. Here we have to observe that C is a scalar and U is a vector, and their product is another vector that will be in V. That is another vector. So this is another object. In fact, objects are called as vectors in vector space. So vector means it need not be a physical vector. It may be a pen, pencil, chemical, signal, or anything. There is an object in a vector space. We denote it by, we call it as by vector. The 7th property is vector distribution. C times U plus V is equal to Cu plus C. We have seen these in ring theory and in fields. So here the vectors are distributed. U plus V is a new vector that is taken C times. That is U plus V, U plus V, U plus V, C times. We will get another new vector that should be equal to U is repeated C times and V is also repeated C times. You will get new vectors. By adding all those things, you will get another new vector. This must be equal to the first vector. That is C times U plus V. This need not be told in all the sets. So, a vector space, this condition, and the eighth property is C plus D times U is equal to Cu plus Du, where C and D are scalars and U is a vector. So here, if the vector is taken C plus D times, that is C plus Du, that is equal to Cu plus Du. That is, the vector is taken C times first, then you will get another vector that is added to a vector which is formed by using U D times. So that is our eighth property. Now the ninth one is C times Du is equal to Cd times U. Here C and D are scalars and U is the vector. So Du is another vector that is taken C times. That is equal to U is taken Cd times. And finally 1U is equal to U, where 1 is the unity in the scalars taken. If all these 10 properties are satisfied by an empty set with the two operations, vector addition and scalar multiplication, then we can say that that non-empty set is a vector space with respect to those two operations. If the scalars are taken as real numbers, if real numbers are taken as scalars, then we can call it as a real vector space. And scalars are complex numbers are taken as scalars, then we can call it as a complex vector space. But for simplicity, we call a real vector space as vector space. If we use the term vector space, it can be understood that we have used the scalars, we have used the real numbers as scalars, unless it is specified. If we specify something, those scalars will be used. Otherwise, we take scalars are real numbers. So hereafter, whenever we are using scalars, they can be considered as real numbers. We can take vectors, we can take scalars as rational numbers also. Rational numbers also can be taken as scalars. That vector space is called as a rational vector space. So you can take the elements of any field as scalars. It is already seen by us. The elements of a vector space are called as vectors. We denote the elements of the vector space as vectors, and the numbers, real numbers or complex numbers, as scalars. So hereafter we use these two terms. One scalars and second one is vectors. I'm going to repeat it again. Vector means it does not represent a vector in physics. It may be a vector, it may be some objects, it is a pen, pencil, everything can be, any object can be taken as vector, provided there must be defined a vector addition and scalar multiplication properly, and those two operations satisfy all the 10 conditions which we have seen earlier. So if all those 10 conditions are satisfied with two binary operations on a set, we can consider the set as a vector space, and the elements of that vector space are called as vectors. Now let us move on to the two concepts. The first one is zero vector. I will call it as O. Zero vector O in a vector space V is unique. So zero vector is unique. By one of our axioms, there must be at least one zero vector. Now we are going to prove that it is unique. There will not be another zero vector. So let us take, there will be another vector. There will be another zero vector in our vector space W, and finally we do that zero. I am calling it as O, of course. O is W. Both are same. If we do that, we can say that there will be only one zero vector. So I am taking two zero vectors. Let O and W be two zero vectors in V. And since W is a zero vector, O plus W is equal to O. So this is the property of zero vector. Zero vector does not change the vector. Here, if W is a zero vector, it does not change O. So it will give you O only. Similarly, if O is a zero vector, O does not change W. So W plus O is equal to again W. Since O is the zero vector. Since we have taken that there are two zero vectors, these two, we can get these two relations. These are seen in the properties of zero vector are seen in axiom number 4. Then I can take W is equal to from this that is W plus O. W plus O is O plus W by commutative property, the second axiom, and O plus W is 0. 0, that means O here, O zero vector. So finally we got W is equal to O. If I take two zero vectors, then both are the same. So we can conclude that zero vector is unique in a vector space. So in every vector space, there will be a zero vector. There will be only one zero vector. That is the point here. Next, another one is the vector minus U called negative of U is unique for each U in a vector space. We have already seen from the axiom number 5 that every vector must have a negative, must have another vector minus U such that U plus minus U is equal to O. Here we are going to prove that negative vector is unique. There will not be two negatives for a single vector. Again, in contrary to our statement, let us take two negatives in our vector space. First, let us take a vector in our vector space V. Let that be U. And suppose there exist two vectors, minus U and minus U dash in V, such that U plus minus U is equal to O and U plus minus U dash is equal to O. So we have taken two negatives. If these two are negatives, these two hold this property. And then we can say that minus U is equal to minus U plus O. We can add zero vector to any vector. It does not affect anything. Here, O can be replaced with this first relation. So minus U plus minus U dash. I have taken the second relation. Minus U dash. And by associative property, we can interchange these brackets. So it is minus U plus minus U dash. That is equal to, we have commutative property. Commutative property. By that, we can interchange or exchange the first two. Minus u means u plus minus u, and that is added to minus u dash. U plus minus u is O from this one, since minus u is the negative, and O plus minus u dash is minus u dash, since O is the 0. So here we got minus u is equal to minus u dash. If I have taken two different negatives for a single vector u, finally I concluded that both are same. So there will be only one negative for each vector in a vector space. Earlier we have proved that there will be only one zero vector in a vector space. Now we have proved that there will be only one negative for each vector u in a vector space. Now let us move on to the properties of vector spaces. We are going to discuss some of the properties. This is the first one. 0u is equal to O for every u belongs to U. This is the property. Simply, you can say that 0 of something, 0 is multiplied by something, you will get 0. But here, this is O, the 0 vector of your vector space. So 0 times any vector is 0 vector. It goes to 0. That is what we are going to do. And after doing this, we can use this result wherever we want. So 0 is a scalar, particularly in real numbers. Of course, we are in real numbers. 0u is equal to 0 plus 0 and u. 0 plus 0 times u. That is equal to 0u plus 0u by our distributive, our scalar distributive property, axiom number 8. At this point, we don't know what is the value of 0u. So 0u is another vector. We have already seen that cu, scalar multiplication, is closed. So if C is a scalar, Cu belongs to V. So here C is 0. 0 is a scalar. So 0u belongs to V. No doubt about it. 0u belongs to belongs to V means it is a vector. So if it is a vector, you can find a negative to that. It is also one of the axioms. So its negative is minus 0u. So if we add minus 0u on both sides, you will get 0u plus minus 0u is equal to 0u plus 0u, which is already here, plus minus 0u. By associativity, you can interchange these brackets like this. That is axiom number 3. 0u plus minus 0u. A vector is added to its negative. Then we will get the 0 vector. 0 vector is O here. So it is O. That is equal to here OU, sorry, 0u. 0 is scalar. 0u plus this 0u is added to its inverse. So it is also 0 vector. 0 vector is O. So finally we got O is equal to 0u plus 0. If some vector is added to 0 vector, you will get the closure vector. So you will get OU on the right hand side. So finally, O is equal to 0u. This is what we require. Hereafter, we can use this. So some vector is multiplied with the 0 of the field. Here we are taking real 0, but in other examples, it may be negative So edit 0 element of A2 identity of the first binary operation in the field. Here we call it as 0. So this is the first property, and now this is the second one. CO is equal to O for every scalar C. Here O is the 0 vector of our vector space. We are in the vector space V, that is not repeated every time. So CO is equal to C times O plus O. Since O is the 0 vector, if you add 0 vector to 0 vector, you will get again 0 vector. It will not change anything. So 0 vector can be written as O plus O. So it is C times O plus O. We have already got the vector distributive law. With that, we can write it as CO plus CO. That is axiom number 7. And CO is a vector in V. So you can find minus CO since V is a vector space. So you can add minus CO on both sides. After adding minus CO on both sides, you will get CO plus minus CO. That is equal to CO plus CO. This is carried to here, plus minus CO is added here. Again, by associativity, we can interchange these brackets. This can be written as CO plus this vector. So instead of adding these two vectors first, we are adding the result of these two vectors to the CO, this vector. This is associative property, which we have discussed earlier. So on the right hand side, this is O. The vector is added to its negative. So it is 0 vector O, and on the right hand side, this is CO, and this is again 0 vector O. So here a vector is added to the 0 vector, so it will give you the original vector 0. So finally, we got 0 vector O is equal to 0. So we can conclude that CO is equal to O for every scalar C. That is, even if you multiply 0 vector with any number, any scalar, ultimately you will get 0 vector only, just like ordinary 0 in real numbers. So in any vector space, that 0 may be sometimes water, sometimes air. It depends on the other vectors and the system, of course. But if you add, multiplying with the scalar means you are adding that repeatedly. Even after adding repeatedly, you will get the same 0 vector in the answer. So that is the property here. Now let us move on to the next result. That is minus 1 times u is equal to minus 2. This is the third result. So here u is multiplied by minus 1. Here minus 1 can be regarded as multiplicative inverse of multiplicative identity. So we can take from our previous results, O, the 0 vector is equal to 0u, 0 in the field, here 0 in the real numbers. 0 can be written as 1 plus minus 1. This is multiplicative identity, and this is inverse of multiplicative identity. If these two are added, we will get 0 in the field. So here we are taking real numbers. easily get 1 plus minus 1 is. So that is multiplied by u here. So here 0 is written as 1 plus minus 1. These two are scalars. We already have the distribution law of scalars. Using that, we can get this is 1u and minus 1. You can also omit this dot. 1u also can be written. This is our answer number 8. From 8, we can distribute this one as 1u plus minus 1. So from the 10th property, that is also crucial. We can write 1u is 3. We already discussed 1 is not usual 1. It may be identity. It is the identity. Multiplicative identity in the 3. So from the 10th property, it is u, and minus 1 times u is carried as this. So now O is equal to u plus minus 1 u. We have already commutative property. With that, we can interchange these two. So I can write it as minus 1 times u plus u from our axiom number 2. So after seeing this, we can conclude that u plus minus 1 u is equal to O. So minus 1 u is taking u to 0 vector. That means minus 1 u is the negative of, it is taking this vector to 0 vector. So it is negative of u. So negative of u is denoted by minus u. Minus u is the symbol for negative of u. So we can conclude that minus u is equal to minus 1 times u. Now observe that minus u is the symbol for negative of u. So this is our third property. So hereafter we can easily convert minus 1 u to minus 3 without any hesitation. In vectors also, that is more important. This holds in vector spaces. So while dealing with objects, chemicals, signals also, the properly defined scalars, when it is a vector space, you can find these results. Once a certificate of vector space is given, you will have the luxury of all these properties in that system also. So now let us move on to one more property. Suppose Cu is equal to O for some non-zero scalar C, then U is equal to O, the zero vector. If U is multiplied by some scalar, and you will get a zero vector. Whenever C is a non-zero scalar, then U must be a zero vector. Here C not equal to 0 implies 1 by C belongs to R. So here we have taken real numbers. So 1 by C defines. 1 by C also defined. It must be an element of R. Even in other fields also, if C is non-zero element, then 1 by C. 1 by C is nothing but multiplicative inverse of C. Multiplicative inverse exists in fields. So 1 by C belongs to that field. So 1 by C is again scalar in our language. Wherever C is non-zero, 1 by C is also scalar. Now Cu is equal to O, the zero vector implies I am multiplying this with another scalar 1 by C on both sides. Then I will get 1 by C Cu is equal to 1 by C times Cu is taken as O, the zero vector. So 1 by C times O, that is equal to O from this one. from the previous property. If 0 vector O is multiplied by some vector, some scalar, you will get ultimately 0 vector only. This is our one of the previous property. So finally we got 1 by C times C. This is one of the associative property related to scalar multiplication. Our axiom number 9. With that, I can exchange the brackets. That is multiplied by U. That is equal to O on the right hand side. We know that 1 by C into C is 1. A multiplicative inverse is operated with the element. Finally, you will get identity, multiplicative identity, that is 1. So 1 into U is U by our axiom number 10. On the left hand side, on the right hand side, you will get this 0 vector. So U is equal to 0. So we can conclude that wherever C is a non-zero scalar, and that C is multiplied to some vector U, and you will get a 0 vector, then that vector U must be 0 vector. So you can't get a 0 vector when multiplying a non-zero vector with a non-zero scalar. So it is not a integral domain. There will not be 0 dividers. So this is the another property of vector spaces. Now let us look into some of the assignments on the topic we have discussed so far. This is the first assignment. Let V be the first quadrant in the xy plane. So V is the set of all points of xy plane, first quadrant of xy plane. That is, in the first quadrant of xy plane, both x and y both are positive. That is what we can hear. V is equal to set of x, y such that x greater than or equal to 0 and y greater than or equal to 0. So this is the first quadrant. I think so. This I will take it. Okay. The problem is if U and V are in capital V is set, is U plus V in V. If you have taken 2 points, U and V are vectors in V. There is nothing but 2 points. If you take 2 points, is U plus V in V. Why? If you take U's relation, then both let U is equal to x1 y1 and V is equal to x2 y2. Then U plus V will be x1 plus x2 and y1 plus y2. This is the second point. Whenever all the x1, x2, y1, y2 are positive, we will get x1 plus y1 is positive and x2 plus y2 is also positive. So the resultant vector is also in first quadrant. So the answer for the part A is yes, since all the elements are positive, all the x, y are positive. Next B, in the part B, find a specific vector U in V and a specific scalar C such that Cu is not in V. So if I take a vector 1, 1, that is a point, I will now call it as a vector. So 1, 1 is a point. If I multiply with a negative scalar, I can use any scalar. If I multiply with a -5, I will get the point -5, -5. That will not be in first quadrant. So here one of our vector space property holds. First property of our vector space is holds good. But this property, Cu, this is of scalar multiplication. Scalar multiplication is not closed. So it is not a vector space. If all the 10 properties holds good, then only we can say that it is a vector space. Even if a single property does not hold, we can say that it is not a vector space. If all the 10 properties are satisfied, then we will give a certificate of vector space. Then the entire theory applies. Whatever we are going to do in the next classes, the theory of vector spaces, will apply to those systems which satisfy all the 10 conditions. Once the system satisfies all the 10 conditions, we call it as vector space, and we do construct the next theory on basing on those 10 axioms. So, in this example, this is not a vector space. The first quadrant of xy plane is not a vector space. And this is another assignment problem. Let W be the union of first and third quadrants of xy plane. You can imagine that. That can be mathematically written as W is equal to set of xy such that xy greater than or equal to 0. So xy both can be positive or both can be negative at a time. In the third quadrant, x and y both are negative, but their product is positive. Of course, in the first quadrant, x, y both are positive and their product is also positive. So this is an expression to tell that it is a union of first and third quadrants of x. So it is a mathematical expression. So now the problem is, if U is in W and C is any scalar, is Cu in W? Why? This is the problem. So you have to take some U in W. W is the vector space. It is given set now. So it may be in the first quadrant or in the third quadrant. If you take in the third quadrant, if you multiply it with any scalar, with any positive scalar, you will get a vector again in third quadrant. Since it is negative again, both the coordinates are negative. If you multiply with a negative number, both the coordinates will be positive and that vector will be in first quadrant. First quadrant is also W now. So this condition holds in W, where W is the union of first and third quadrants. Now the second point is find specific vectors U and V in W such that U plus V is not in W. So here we have to show that it is not closed under vector addition. So you have to choose some vectors U and V such that the addition, the resultant vector is not in this union. So let us take x coordinate as 1 and y coordinate as 5. 1, 5. 1, 5 is my U, and -3, -2 is V. So both are in W. 1, 5 is in the first quadrant, and -2, -5, -3 is in third quadrant. But the resultant vector 1 plus minus 2 is minus 1. And here 5 plus minus 3 or minus 2, that is 2. 1 positive, 1 negative. So it is in the second quadrant. That is not in the. So that is example for U and V.